Greetings all, and today again I'm here with another beautiful topic, which is half-life. And half-life is common topic in nuclear physics, and there are calculations and as well as derivations I just want to clear out. And there are formulas which every student that masters those formulas, that student is totally safe with any calculation that regards or that relates to half-life in terms of WASCCE level, NECO, JAMB, and other related examination for senior high school. So half-life, before we move to half-life, we need to consider radioactive decay law. A radioactive decay law is just telling us about is when the probability per unit time is proportional to the number of nuclei present. So in this case, this law is just telling us the probability when the probability per unit time is directly proportional to the number of nuclei present. In this case, we have this probability dn all over dt is directly proportional to the number of nuclei present. That the relation or the law is telling about dn all over dt is directly proportional to n. So in this case, if we remove this proportionality, we are going to have a constant, and that constant is what we call the decay constant. And what do we mean by decay constant? Decay constant is just defined as the rate of radioactive nuclei per amount of nuclei present at that time. This is what we just mean by decay constant. And another term again, which we just have to consider, similarly, it's simply the activity. And the activity, or we can also call it the rate of decay, is defined as the amount of radioactive nuclei that decay per time. And we have various units, which have the count rate, the pulse per minute, and we have again the number of simple atoms. So those are some of the various units of simple activity. So in this case, we focus on half-life. What do we mean by half-life? So half-life simply means is the number of times radioactive takes place to decay to half of its initial or its original value. Number of times for the radioactive substance to decay to half of its initial or original value is what we refer to as simply half-life. And there is a relation that connects with this half-life, which is T half, and the decay constant, which is lambda. So that relationship, we have it to be half-life to be ln 2 divided by the decay constant. So how can we be able to arrive to this relationship? So these are our points of concern, how we can have this. And these formulas we are going to derive here, they will help you to solve any question regarding nuclear physics under half-life. Questions regarding to NECO, WASCCE, JAMB, and other related. So short, if we recall to the radioactive decay law, which tells us that the rate of decay, the probability of rate of decay is directly proportional to the number of nuclei. So if we consider this relation, let's just say we try to have the derivation in this point. So if we have the derivation in this point, we say the probability per decay time, dn all over dt, is directly proportional to the number of nuclei that's present at that particular time. So if we remove this, we have dn all over dt to be equals to lambda. Lambda is a constant, and we add our n. And we're going to have a negative sign. The negative sign is just telling about how the number of nuclei present is related to the time. You see, the higher the number of nuclei present, the lower the time. Or the higher the time, the lower the nuclei. Which, the end of the day, we are going to plot the graph of how the nuclei n is related to the time. because the graph is going to be an exponential graph. Wherein this portion is just telling about the t half, since it's the time, and here is just telling about the n, and this point is going to be NO. But this n is equals to NO all over 2. But we are going to consider that before the graph ends. So the minus sign, I know you capture how the minus sign is. The meaning of the minus sign tells us how the number of nuclei present is related to t. Now, how can we be able to have a beautiful derivation for half-life? Now, you know we have the n here. N is here, n is here. We'll try to collect like time. In doing that, this dt will move towards this side, and this n will move towards this side. So if we interchange n and dt, we have the n all over n equals to negative lambda dt. This is one way. So now, since we are trying to have a derivation, we apply integral, we integrate both sides. We say apply integral sign. So if I apply the integral sign on both sides, it's going to be the integral of 1 all over n. We have our dn. We'll factorize the decay constant. We'll take the integral of this. But in this case, the decay constant will be the initial value or the original value to the final value. You see, so NO is the initial or original value, and N is the final value. So NON 1 upon n dn equals to negative lambda or the decay constant and integral of dt. But mind you, if we integrate 1 all over x in terms of derivative of x, is going to be ln x. We have to capture this. Similarly, if you integrate 1 upon a, the a is going to be ln a. If you integrate 1 upon p in terms of derivative of p is going to be ln p. We have to take note of that. So in simple sense, if we integrate 1 all over n, the n, we all know is going to be what? Ln n. So we have to take note of this. So if we apply this sense, which we have over there, if we integrate 1 all over n, so definitely it's going to be ln n. Don't forget, we have our limits here. The limit, the initial, which is NO, and the final, which is n, equals to negative lambda. If we integrate dt, is going to be the variable t. This is what we have. And since we have our limit, we substitute our limit. We start from the top limit, and later we consider the lower limit. If we consider the top limit, which is ln n, and we consider the lower limit, which is NO, equals to negative lambda t. So moving forward, we have logarithm. As a science student or as a mathematician, if you have log a plus log b, since we are adding, we can take one log, we multiply the values. So it's going to be a times b, which is ab. Similarly, if we have the same log, but we are subtracting, we take 1 and we divide. So there is something again we have here. And ln and log, they are almost the same, they are related. So if we take ln here, so it's going to be the first value. Since we have the minus sign here, we divide it by NO, equals to negative lambda t. So in this case, it's just like how we can extract a number from a log. How can we simply extract a number from a log? In less than 2 seconds, just maintain this number, and the base b will power this constant c. So it's going to be a equals to b raised to power c. We'll do the same thing. This number, if we remove the, going to be n all over no. In this case, we are going to take the exponential of both parts. So it's going to be the exponential e raised to power negative lambda t. This is what we have. You see? So if we make n the subject, we'll cross multiply, because this can be over 1. N times 1 is going to give us n, and n times is going to be no e raised to power minus lambda t. So this is how we have it here. So this is one of the equations we have to consider. You see? So in half-life, we have this n is the number of nuclei, which is the final value. This no is the initial. This lambda is the decay constant, and the time is the time and a substance takes to decay. You know, the negative sign shows the relationship between the nuclei present N and the time. The higher the time, the lower the nuclei present. The lower the time, the higher the nuclei present. So we have this. So in another version, we try to have simple formulas without using, because most times if you try to use this formula, it's somehow complicated. So there is another version way of solving these half-life problems without using this formula. So how can we have those short formulas? We have to take note of this. But for define half-life, half-life tells us that it's the number of times a radioactive substance takes to decay to half of its initial or original value. In this case, for half-life, which you can represent as T half, straightway N is going to be half of its initial value. Like when you are solving problems, you know, we have the initial value and we have the final value. Definitely, this NO, we have to take note, is always greater than this value. Now, let's say we have a decay mass of 10 grams. Let's say 15 grams as the initial value, NO. So when this decay to half of its value is going to be 25, then the new value is going to be N. We can see that NO will be greater than N. The same thing again, if we come here again to this version, this is going to be an NO. If this disintegrates to half of its original value, it's going to be 12.5 grams. So this is going to be N. So you can see in a version that always NO is greater than N. So in this case, NO is greater than what? N. You see? So therefore, if we cross multiply here, we have NO to be 2 times the final nuclear that's present at that particular time. So if we recall from this formula, we say N equals to NO e raised by minus lambda T. I hope you get that. Now, we have N equals to, what is NO is 2N e raised by minus lambda T. We can see N carefully cancel N. So we have 1 equals to 2 e raised by minus lambda T. So divide both sides by 2, we have 1 over 2 equals to e raised by minus lambda T. You see, we have again the exponentials or the inverse of a value. 1 upon 3 can as well be written as the inverse of 3. 1 over 4 can as well be inverse, can as well be written as the inverse of 4, which is 4 raised to power minus 1. And 1 over 2 can as well be written as 2 raised to power minus 1. So this 1 over 2 is the same as 2 raised to power minus 1 equals to e raised to power minus lambda T. Since minus here is minus here, this minus cancels this minus, so we have 2 equals to e raised to power lambda T. So this is the version. So in another case, if we proceed here, we apply link both sides, take link on both sides, take link on both sides. So if we take link on both sides, it's going to be link 2 and link this. So doing that, we have link 2, which equals to ln of the exponential of e raised to power lambda T. So if we move this lambda, we have ln 2 equals to lambda T ln E. You see? But there is a point which we have to capture here. The moment we use half-life, this T automatically becomes T half. You see? So this T automatically becomes half-life. This is half-life because we use the condition of half-life, which tells us that the number of nuclei present is originally half of its original value. You see? So this T automatically becomes half-life, half-life, half-life. I hope we capture that. So this automatically becomes half-life, half-life. So our target is how we can have this half-life. So now we divide both sides by, because we are looking for lambda, but we have to take note of that. Let's rewrite this. Note, ln e raised to power 1 is always 1. We have to take note of that. So therefore, if we write, we have ln 2 equals to lambda T half, because e raised to power 1 is, ln e raised to power 1 is 1. So therefore, if we are looking for T half, we divide both sides by lambda, so ln 2 equals to lambda T half. Divide both sides by lambda, both sides by lambda, this cancels this. So therefore, this implies T half equals to ln 2 all over the wavelength. So this again, another formula I want us to capture. So the two formula I want us to capture for now, we have this, the nuclear present n equals to NO e power minus lambda t, and this other one again, the half-life or T half equals to ln 2 all over lambda. So these are sensitive formulas I want you to capture. So if we move again, to proceed to have another relations we have to find. Here now we have to take note of that this T half is in relation to the decay constant. How half-life is related to decay constant lambda. So we are looking for another simple way of using half-life calculations problems or formulas. So in this case, we recall again n equals to NO e to the power minus lambda t. You see, let's try to have another derivation. We have n, we divide both sides by NO, which is NO equals to e to the power minus lambda t. You see, now if we reciprocate, if NO move up and n comes down, we say NO all over m. This will maintain constant, but the negative side will disappear. So we have it as lambda t. So in this case now, let's R equals to T to the power n equals to NO all over n. That means we have see NO all over n, either we let it as R or let it as 2 to the power n. Where this 2 to the power n is telling about the disintegration rate. You see, NO all over n is the disintegration ratio. The disintegration ratio is same as N all over n or 2 to the power n or R. So this NO all over n will represent it as 2 raised to the power n equals to e raised to the power lambda t. But 2 to the power n equals to e raised to the power, but we have lambda. Let's make lambda the subject here. If we make lambda the subject, we have ln 2 all over T half. You see, we have ln 2 all over T half. So if we have ln 2 all over T half now, so we say this lambda is ln 2 divided by T half equal ln 2 divided by T half times T. So which you can as well be written as 2 to the power n equals to e raised to the power. Yes, let's make ln 2 the subject. We can say e to the power ln 2 times T divided by T half is what we have. So if we put it in another easy way, we can say it's just like if you have a raised to the power b times c, we have the right to say a raised to the power b all raised to the power c. Because all these numbers are powers, you can put either one inside the bracket. So if we apply the same logic here, 2 raised to the power n will be equals to, or in a simple form, let's just maintain this as NO all over n. You can use the concept later. So if we maintain it as NO all over n, we have something like e raised to the power ln 2 all brackets T all over T half. So now, if you use your calculator, if you take your calculator, e raised to the power ln 2, this is again another concept you have to capture. E raised to the power ln 10 is always 10. Logarithm. You have e raised to the power ln 5, the answer is 5. If you have e raised to the power ln 7, the answer is 7. So the same thing, if we have e raised to the power ln 2, the answer is 2. You know, it is in brackets, and we maintain our T all over T half. So in this form, we can say let's, as what we did here, right? Let n equals to T all over T half. So we have T all over T half represented as n. So this equation becomes NO all over n equals to 2 raised to the power n. This is again another formula you have to capture. So the formulas I want you to capture, we have the first one, we have two, you have the first one which I have cleared, wherein you have n equals to NO e to the power minus lambda t, this again. And also this again is also must be captured. You see, so these formulas, I want you to capture them. So the letters, I know NO is the initial or the original value, and N is the final value. This N is just, this 2 to the power n is the same as R, which tells us about the disintegration ratio. So now, since we have this, if we want to have the last formula, which we can use to solve any half-life question, the next point, we recall again this same relation. You see, if we recall this same relation, also n equals to NO e to the power minus lambda t. So if we make n the subject, say n divided by NO equals to e to the power minus lambda t. So since we have this value, if we interchange, we have NO all over n equals to e to the power lambda t. You know, when we interchange, you see. So I told you NO all over n, NO all over n, the same as 2 to the power n, which is the disintegration rate, or R. So we represent this n all over to be R, the disintegration ratio equals to e to the power lambda t. You get that? So now, if we take ln on both sides, or log, we see log R equals to log e raised to the power lambda t. So we maintain log R equals to, we move this power, which is lambda t log e. So having this now, we'll make lambda the subject. If we make lambda the subject, it's going to be lambda, it's going to be log R divided by lambda t log e. So in this case, we can summarize it as lambda, or the decay constant, equals to 1 all over log e times log R divided by t. So wavelength now. Now what is the value? What's the value of 1 divided by log? 1 divided by log the exponential of e raised to the power 1 this. So we have the value to be 2.302585. Let me stop there. Log R all over t. You see? So this again another formula I want you to capture in a simple form. So I think these are all the formulas I want you to capture. So let me just summarize them in summary. To solve any half-life question, you have to take note of 2 raised to the power n equals to NO all over n. This is the first formula. And the second formula, we have this we can take it to 2 decimal places or 3 decimal places. Lambda equals to 2.303 log R equals to t. This is formula 2. And the next one, we have again the half-life, T half equals to ln 2 all over the decay constant, which is 3. And we know the original one, which is n equals to NO e to the power minus lambda t, 4. And the last one, we have n equals to t divided by t half. T divided by t, this is equation 5. This is the 5. So the next one again, so you have to take note of, to solve any half-life question, you have to know this 2 to the power n is the disintegration ratio, which can as well be simplified n all over n. Lambda equals to 2.303 log R all over t. You know this R is the same as this 2 to the power n, which is the disintegration ratio. And we have the half-life to be ln 2. But ln 2, if you can take your calculator, ln 2 will give you something like 0.693. You can substitute ln 2 to be 0.693 divided by wavelength. Some books you might see that. And we have the nuclei equals to NO e to the power minus lambda t, and n equals to t all over t. So when you master this, you can solve any question regarding to half-life. This is the basic. So when those formulas are mastered, there is no question for WASCCE level which you will not able to solve. So the last part now, how we can have the relation graphs of nuclei and nuclei and the activity present in terms of time. Activity present in terms of time. So sometimes you might be asked, so let's say the first graph n against, let's say nuclei present against time t. So the graph would look like in this way. T, this is the nuclei present n. So the graph is going to be simply by an exponential graph. An exponential graph is a graph that varies very rapidly with t. That this n very rapidly with t. So if we have the half-life, this is the point where we have half-life. So here is t half, and this point is going to be the initial NO, and it is going to come here. Here is n, but this n here is equals to, half-life is NO all over n. So if you are asked to draw a graph of the nuclei present against time t, this is how you are going to draw the graph. The same thing again, if you are required to draw the same graph again in terms of simply the activity A with respect to time in seconds. So the graph again, the same thing, is going to be an exponential graph. This point, we have this to be t half. This point is going to be AO. This point is A, but this A is same as AO all over 2. Since we can write the equation of n to be NO e raised by minus lambda t, we can as well write again, n equals to NO e raised by minus lambda t, and the activity again, A equals to AO e raised by minus lambda t. And this graph is plotted as AO. Here is AO, which is the initial point, and the final point is A. And this A is half of the initial original, which is NO. Here is the same thing, NO is the initial, this is N is the final, and this final is half of, here is going to be half of this. So this is just the graph of nuclei present and against time. So thank you for watching. I hope this video will make sense to you.